Are you wondering what I'm doing with a magnetic field sensor and a magnet? Oh, I bet you are. And let me tell you, I am so excited. Check it out. We've got, yeah, that was weird. I'm sorry. I'm just a little excited about getting into something new. So this is the sensor. This little white thing. I have to make the magnetic field pass through it. Here's a bar magnet. I'm going to get that sensor about roughly 2 centimeters away, and you can see it's roughly 4 millitesla. All right, stands for Tesla. That is our unit of magnetic field strength. It's pretty big, a Tesla, so that's why we're at just looking at milliteslas. Now, if I jump out here and I double the distance, check that out. The magnetic field strength just dropped by a factor of 4. I've seen that somewhere before. I know I have. Yeah, that's right. It was magnetism and electrostatics. So all these these natural forces are following this inverse square law for distance. And if you remember from when we looked at electric fields, right? It's just a construct. But we're also going to look at the same kind of thing for a magnetic field. So I want to see what the magnetic field would look like surrounding this bar magnet. And so what I'm going to do is I'm going to use a compass to do that. So here's a compass. My son is a scout, so he had a compass ready to do some orienteering. And you know that the needle of a compass aligns with the magnetic field of the Earth, right? And let's just take a look at how that's how a compass works. And so if I put this compass around my magnet, I should be able to map out what the magnetic field looks like around the Earth. I'm sorry, around the magnet. Wow. All right, so check it out. Wait a minute. I thought the needle always pointed to north, but looks like the needle is always pointing away from north, and it's always pointing towards the South Pole. That's pretty crazy. Wait a minute. Have I been lied to all my life? Wait a minute. So this is always pointing towards, oh, I'm sorry, away from magnetic north. Let's come back to that in just a sec. I want to look at something else first. I want to look at the shape of this this magnetic field. And what I'm going to do is I'm going to take these iron filings. They're just little pieces of shaved iron. I'm going to sprinkle them over top of this magnet. Okay, you can see the outline of the magnet right there. Tap that a little bit. Look at that. Can you see how it's moving just from one pole to the other? And in the middle, it's like a continuous line straight through. What you probably can't see is the fact that these iron filings are not laying flat on the paper. They're actually coming up. And that's because they're aligning with the magnetic field. They're acting like a bunch of tiny little magnets. And that magnetic field is not just in the plane of the paper. It's in 3 dimensions. It's completely surrounding that magnet in every direction. Okay, so let's take that back to look at what the magnetic field looks like around the Earth. Right? If I've got Earth here, and well, let me grab that. There we go. Yeah, look, I've got Earth, right? It's almost as if someone's taken a great bar magnet and shoved it through Earth. And I've got the South Pole, the magnetic South Pole, close to, but not exactly on the axis, the North Pole. So that when I bring a compass to any point here on the surface of Earth, it's going to point pretty much in the direction of geographic north. Okay, if I bring it over here, right, it's going to point towards geographic north if I'm there. So you got to keep those two things straight. That there are these field lines that your compass is aligning with, that's pointing always in this direction, which is towards magnetic south, which is close to geographic north. That's kind of trippy. And the thing is, there's some degree difference. It depends where you are, between where this pole is and where this pole is, so that your compass doesn't necessarily point at true geographic north, right? And the airstrips, what they do is they make all the airstrips numbered so that they know how many degrees difference that is, and that's why they number them that way. It's not arbitrary. So one other thing you guys should know is considered like the fundamental law of charges, where we had opposite charges attract and like charges repel. This is the north end, and this is the south end. If I bring it close, what do you think is going to happen? Yeah, it's attracted to opposite poles. If I bring this in this way, bring them closer, what's going to happen? You guessed it. It was repelled from the north and attracted, repelled from the like pole and attracted to the opposite pole. I hope that that was interesting, at least a little. So let's recap. What are the three things we know? Those are three fingers. One thing we know, that magnetic field strength is going to have an inverse square law, follow an inverse square law with distance, so it's going to get weaker as you get further away by the square of the distance. Two, that it always points, the magnetic field lines always point away from north, and so they exit the north side and they enter the south side, and that like poles are going to repel while opposite poles will attract.